and this will be our last lecture for Chapter 4, where we talk about counting rules 4.4. Key concept. So this section requires much greater use of formulas as we consider 5 different methods for counting the number of possible outcomes in a variety of situations. Now, not all counting problems can be solved with these 5 methods, but they do provide a strong foundation for the most common real applications. Multiplication counting rule. The multiplication counting rule for a sequence of events in which the first event can occur in 1 ways, the second event can occur in 2 ways, the third event can occur in 3 ways, and so on. The total number of outcomes is the first number of ways in 1 times the second number of ways in 2 times the next number of ways, and so on. So an example, a hacker guessing a passcode. When making random guesses for an unknown 4-digit passcode, each digit can be 0, 1, 2, 3, onwards to 9. That's 10 digits altogether. What is the total number of different possible passcodes? So given all the guesses have the same chance of being correct, what would then be the probability of guessing the correct passcode on the first attempt? Well, like our rule for the multiplication counting rule, if the first event can occur in ways, let's ask ourselves how many events here. A 4-digit passcode is, you could think of it as a compound event. It's comprised of 4 events. The event of guessing the digit for the first digit, and the next event would be the guess for the second digit, the third digit, and the 4th digit. So 4-digit passcode, 4 events. And each digit is 0, 1 through 9. So that means we have the total number of ways of guessing the first digit would be 10, since there's 10 total digits. Now the next digit could be the same as the first one, so it's not like we're removing the possibility if you had a 0 here first or a 3 here first, then you couldn't repeat that. So the numbers can be repeated. That's a key idea here. So the next number, there's 10 possibilities. The next digit, 10 possibilities. The next digit, 10 possibilities. And this is 10 to the 4th, which is 10,000. Which means that if your ATM card is stolen and it has a 4-digit PIN, there's a 1 in 10,000 chance probability that hacker guesses PIN is, there's only one correct PIN out of the 10,000 possibilities, so 1 out of the sample space of 10,000, or 0.00001. Oh, excuse me. 0.0001. Right. Next, we'll consider the factorial rule. So the factorial rule, the number of different arrangements, order matters here, of n different items when all n of them are selected is n factorial. And n factorial means whatever integer, it has to be a positive integer. Whatever integer you have times the one just before it. So it's kind of a countdown multiplication. So then the next number before that would be n minus 2. And then down the line until you get to 3 times 2 times 1. We have a special convention that 0 factorial is equal to 1. So the factorial rule is based on the principle that the first item may be selected in different ways, and the second item may be selected in minus 1 ways, and so on. This rule is really the multiplication counting rule, but it's modified for the elimination of one possibility or item on each change of event. So a statistics researcher must personally visit the presidents of the Gallup, Nielsen, Harris, Pew, and Zogby polling companies. Questions are, how many different travel itineraries are possible? And if the itinerary is randomly selected, what is the possibility that the presidents are visited in order from youngest to oldest? So suppose we wanted to visit just Obama, Bush, and Clinton, former U.S. presidents. So first president could be Obama, Bush, Clinton. Now, if you visit Obama first, then that would leave you with two possibilities for your second visit. Bush, Clinton. Right? So if you visited Bush first, you could then visit Obama. Write the names above dots. And then you could visit Clinton. And then if you visited Clinton first, you could visit Obama. And then Bush. Then, well, once you start with Obama and then visit Bush, then you have to visit Clinton if you're visiting all three. Likewise, Obama, Clinton, well, that gives you Bush. Bush, Obama, Clinton, Bush, Clinton, Obama. Clinton, Obama, Bush. And finally, Clinton, Bush, Obama. So the different itineraries would be these individual lines. So this would be an itinerary here. First itinerary would be Obama, Bush, Clinton. So you start off with 3 possibilities. First visit, 3 possibilities. And then your next visit, that narrows it down to 2 possibilities. And then your last visit, your third visit, well, there's only 1 possibility. So you start at Clinton, there's 2 possibilities. You start off, there's 3 possibilities. Obama, Bush, Clinton. Once you've visited one of them, then there's 2 possibilities. And once you've visited your second, there's only 1 possibility. So this would be 3 factorial, or 6 itineraries. So back up here, for A, how many different itineraries are possible? Well, we have 1, 2, 3, 4, 5 different presidents. So once you say you visit, it doesn't matter which one you visit first. The first one, you could start at any one of those presidents. So there's 5 possibilities. But once you choose one to start with, that narrows it down to 4. Okay. So say we chose Gallup first, but then we chose to visit Harris. So after our second visit, that narrows it down to 3. Okay, say we chose Pew. Then there would be 2 left. And then only 1. 4th and 5th. 5 times 4 times 3 times 2 times 1 is 5 factorial, or 120. So if the itinerary is randomly selected, what is the probability that the presidents are visited in order from youngest to oldest? Well, assuming they all have unique ages, that they all have different ages, then there's only 1 itinerary that will be correct. So 1 out of 120, because there's only 1 itinerary that visits by order of their ages. And you divide that by possible itineraries. So counting rules are very useful for determining sample space sizes, and also for determining the number of special events that comprise a given event. So they're crucial for calculating probabilities. So here's an example of a counting rule, the permutation rule. Permutations of items are arrangements in which different sequences of the same items are counted separately. Now it's key that the letter arrangements are all counted separately, whereas for combinations, order does not matter. Because these rearrangements of the letters A, B, and C are all considered the same combination. So here's a few mnemonic devices. P, permutations. P, position. C, combinations. C, committee. So position matters for permutations, but combinations, think like a committee. So in a committee, everyone's equal, and there is no way of arranging items that are, people that are all equal. The permutation rule. So we use this notation, N permute R, which gives us when we have N different items and we want to take R of them and then find the number of permutations we can make of those R objects, we use this formula. So in a horse race, a trifecta bet is won by correctly selecting the horses that finish first and second and third. So first, second, and third, that implies 3 events. Three events to choose. And you must select them in the correct order. You must select them in the correct order. That means order matters. Order matters, so we need permutations. The 140th running of the Kentucky Derby had a field of 19 horses. So this 140 here is to confuse us. Really, there's a field of 19 horses, means there's 19 total. To choose from. Okay. So you could select any 3 horses, but then you have to choose which order they finish, which we saw that if you were to choose 3 things, and if you had 3 things and you all the possible permutations was 6 from our example with the ABC arrangements of the letters ABC. So here we need this is N is equal to 19. So it's 19. And the number of things that we're selecting, R, is equal to 3. So it's the number of permutations of 3 things from a set of 19 things. So from our formula, we get 19 factorial divided by the factorial of 19 minus 3. So that's 19 factorial, and we do the subtraction first. 19 minus 3, 16. Now, what is the meaning of 19 factorial? It means 19 times 18 times 17 times 16 times 15 times 14, all the way down. So times 15 factorial. We'll expand the first four numbers we multiply and leave the rest in factorial notation. And then 16 factorial. Now actually, since we have 16 here, we only want to go to 16 factorial here. So the 16 factorials cancel, and we're left with 19 times 18 times 17. So that is 5,814. That's the total number of trifectas that you could choose from. So the probability of winning this bet is 1 over 5,814. So we've answered this 5,814. If a bettor randomly selects 3 of these horses for a trifecta bet, what is the probability of winning? So the probability of winning trifecta bet. Well, there's only one winning trifecta, and there's 5,814 possible trifectas. So 1 divided by 5,814 is 0.0017. Seven, 1. No, actually the decimal's there. So we would move it 1, 2, 3, 4. Okay, very unlikely. Here's a tricky one to remember, the permutations rule. So this is when some of the items are identical to others. So the number of different permutations when n items are available, and all n of them are selected without replacement, but some of the items are identical to the others. So I'd like to do an example here. The word balloon. So what are the possible permutations of the letters that spell balloon? B-A-L-L-O-O-N. Well, n items are available, so we have n equal to 1, 2, 3, 4, 5, 6, 7, the number of letters that make up the word. But 2 of the letters are repeated. So n1 is equal to 2, the letter L, and then another letter, O. There's 2 possibilities, so 2. So the answer to this problem be n factorial over n1 factorial, n2 factorial. So 7 factorial over 2 factorial over 2 factorial, which would be 7 times 6 times 5 times 4 times 3 times 2 times 1. 2 factorial is 2, and 2 factorial is 2. So we would have 4 here. So the 4's cancel. Then we would have 7 times 6 times 5 times 3 times 2, 2,520. Balloon being one of the possibilities. So an example, what are the possible permutations of 2 heads and 2 tails from flipping a coin 4 times in a row? So that's coin 1, coin 2, coin 3, coin 4. And 2 heads, 2 tails. Well, that's 4 factorial over 2 factorial times 2 factorial, which is 4 times 3 times 2 times 1 over 2 times 2, which is 4 times 3 times 2 over 4. The 4's cancel, and we get 6. And if you recall from lecture 4.2, we had, when we flipped a coin 4 times, we went through all the different possibilities, and for 2 heads and 2 tails, we had heads, heads, tails, tails. Heads, tails, heads, tails. Tails, heads, heads, tails. Tails, heads, tails, heads. Heads, tails, tails, heads, and tails, tails, heads, heads. Let's look at an example involving designing surveys. So when designing surveys, pollsters sometimes repeat a question to see if a subject is thoughtlessly providing answers just to finish quickly. For one particular survey with 10 questions, 2 of the questions, so let's keep track of what we have here, 10 questions total. 2 of the questions are identical to each other, and 3 other questions are also identical to each other. So for this survey, how many different arrangements are possible? Well, we have 10 total. And then we have 2 repeated possibilities. So keep this color coding scheme. N1 equals to 2 possibilities, 2 repeated possibilities. And then we have 3 repeated possibilities. For a different question, type of question. So that's the total divided by 2 factorial times 3 factorial. Which is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, but oftentimes we don't write the 1 since we don't need to. And then 2 times 1. I'll write it here for educational purposes. And then 3 times 2 times 1. So 2's cancel, 3's cancel, and then a factor of 2 will cancel with the 4 here and leave a factor of 2. So we get 10 times 9 times 8 times 7 times 6 times 5 times 2, or 302,400 possibilities. Is it practical to survey so many subjects? No, that's a lot of footwork. So we'll see that typical surveys, the number of respondents is somewhere around 1,000, for reasons we'll discuss later in the course. All right, the combinations rule. Here's our formula. We often say n choose r. So given n things, how many ways can you choose r of them? And the order does not matter. So now we'll see an example of combinations rule. So in California's Fantasy 5 lottery game, winning the jackpot requires that you select 5 different numbers from 1 to 39. And the same 5 numbers must be drawn in the lottery. So the winning numbers can be drawn in any order. That's key. Any order. Is one way of phrasing order doesn't matter. So combinations. All right, so there's 1 to 39 total numbers. So the total possibilities is n. Let me use colors. So n is equal to 39. And there are 5. Select 5. So R is what you're selecting. So R is 5. So how many different lottery tickets are possible? That would be the combinations of 5 things from 39 things. So that's equal to 39 factorial, excuse me, over 39 minus 5 factorial times 5 factorial. 39 minus 5 is 34. So we have 39 times 38. Whichever your largest factorial is in the denominator, that's what you want to expand your top factorial out to. So 39 times 38 times 37 times 36 times 35 times 34, and stop there. 34 factorial, because we have 34 factorial in the denominator, and then a 5 factorial here. So 34 factorial cancels top and bottom, and then we have 39 times 38 times 37 times 36 times 35. Wow, that's a lot. 69,090,840 divided by 5 factorial, which is 120. And still a lot. So there's 575,757 winning lottery choices. So find the probability of winning the jackpot. Well, there's only one combination that will work. So that's 1 over 575,757. And there you have it. Typical lotteries rely on the fact that people rarely know the value of this probability and have no realistic sense for how small that probability is. This is why the lottery is often called a tax on people who are bad at math. Well, maybe that's not so kind to say. Alright, tune in for, we'll go through some problems in the next video.